a little bit of context. I reused a template that I used, and this, what you're seeing there is an iconic building from my university. That's the Portico building. So nothing special other than that. And yet today I'm going to talk about a problem that has to do with offline policy learning from log data. So I'll say what that means in a moment. I'm going to just briefly say something about a few works that were there for a specific setting where the rewards for points are known and which kind of motivated, triggered this project at the beginning. Then I'm going to talk about the specific setting of interest for this research, which is when there are, yes, I'll make an effort to do that, when there are data with rewards, data with known rewards data, and missing rewards data. I'll also say what that means in a moment. And the proposed learning objectives for that setting and some demonstrations. Just a quick snapshot about the experiments. So a quick overview of what this is about. The context is, or the setting is learning a policy. Try to have in mind a recommendation policy, for instance. So there is a set of contexts and there is a set of actions. The set of actions is usually a finite set. It's typically not a large set, but a set of contexts could be, a finite dimension, a set in a finite dimensional space. And then there are rewards that assigns real values to pairs of contexts and actions. And there is a logging policy. So in this setting called logged data, the learning of a policy happens on data that is stored somewhere. Imagine data stored in a server somewhere, but the data is not generated online. The data is not generated as the learning process goes, but the whole data, this batch data that is somewhere stored, that is what is called log data, and that's why it's an offline learning setting. So there is a logging policy that may be partially known or completely unknown in some cases, but that's the data that was responsible for, that's the policy that was responsible for the data that is logged. And then the goal is to learn some policy, let me call it a parameterized, let me call it a parameterized policy, because in practice what we aim to learn is, the parameter values corresponding to that policy according to some particular model. And the quality metric for a policy is this risk notion, which is the expected reward. Expectation means with respect to the randomness in the choice of actions from the corresponding policy whose quality I'm trying to assess with this risk notion, and the choice of contexts from a given distribution over context. So let's think expected reward. Moving on. The previously considered setting, so the works that existed in the literature before this research started, dealt pretty much exclusively with the setting of, let's call it known rewards data. And what I mean by that is that the data, each sample point in the data contains like 4 components. One is, context sampled, and then the corresponding action taken, something called a propensity score. The propensity score is the probability assigned to that action conditional on that context by the logging policy. We may not have access to the logging policy. That's something that I said. The logging policy may be partially unknown, but we assume that the propensity scores are known. So we may not have access to the policy, but we assume that we know the propensity scores at least. And then the last component in this tuples is the reward. So, Ri being the reward, the value of the reward function corresponding to the ith, pair of context and action in that data set. And here is an overview of a few, 3 important works that existed in the literature back in somewhere, when was it, 2015. There was this paper, batch learning from log-bandit feedback through counterfactual risk minimization. So this paper proposed this framework that is called in the literature counterfactual risk minimization, and that influenced how we were thinking about the new setting that we tried to approach. There was then this paper a few years later. This is from 2018 ICLR, I think, deep learning with log-bandit data. So what happened here is that then the models for the parameterized target policies were neural networks, or deep neural networks. That's why the name. And then this other work, it's called Bayesian counterfactual risk minimization. They use actually a pack-based bound and applied it to the risk, to that risk notion for policies in this setting. So those works influenced, kind of motivated the start of this project. And I know that these lectures have been recorded, I think. So acknowledgement and respects to these sets of authors, of course. And so the beginning of the work that I want to present today is, what if we have the same kind of data as those previous works? So there is a set of data that contains context, action, propensity score, and reward. So we like to call it the known rewards data. And additional to that, there might be access, there might be availability of another data set which contains context actions and propensity scores, but no rewards for some reason. The rewards are not there. And the question that motivated this research was, well, we know from previous works that we can learn a policy, and there are different methods to do that, from data of this kind, known rewards data. If I have that, and additionally I have the unknown rewards data, the missing rewards data, can we learn a policy, a better policy, by using the second kind of data, additional to the first, than the policy that we would learn by using only the first kind of data? That's pretty much the question that we wanted to address. So in order to learn policies, there are some risk notions, and these risk notions, it is just a bit quick overview of a bit of the math formalities behind these methods. There is something called the IPS, as the inverse propensity score. Is the reciprocal, the multiplicative inverse of the propensity scores, of the conditional probabilities according to the login policy. So pretty much there are some weighted rewards. The rewards so there is this is an average, an empirical average. We can associate this quantity to an empirical risk. So this is an average. The quantities being averaged are the rewards, but they are weighted by these factors, and these factors are the importance weights. They're known as importance weights in other literature. So that's that notion. It is known that the importance weights, notice that the propensity scores are at the bottom here. These conditional probabilities according to the login policy, pi naught, are at the bottom. That introduces a lot of variance if those values are too small. So sometimes there is this idea of thresholding the denominator to keep it away from 0. So you introduce a positive number to separate those probabilities from 0. So you max between the probabilities and that threshold in order to keep the variance on a leash. And that corresponds then to this truncated IPS estimator for the risk. And now that we're talking about weighted importance weights, a little bit of advertisement. There is a talk that is going to happen tomorrow about how to do importance weights right. Important weights done right, I think that's the title of the talk, by Gergely New. I very much recommend that you follow it if you are interested in these things. So these are the risk notions, and in our work we proved a bound. It's one of those bounds that we call a high probability bound. I don't want to dwell too much on this. It's just to say that we did a bit of theory. We did a bit of math, and a nice result came out. A high probability amount, the high probability part is controlled by this log 1 over delta, the 1 over delta here. So you set like a confidence value, delta is typically a small number, and then this bound holds with high probability, meaning with probability at least 1 minus delta over the randomness. And there are all these quantities involved here. Here is the truncated IPS estimator for the risk. So it's empirical, it can be evaluated on data, that's the important part. In the upper bound, everything can be evaluated from available data. The quantity being upper bounded, so the thing on the left is inaccessible, due to many reasons. And another important part is these terms that come up in the upper bound, the KL divergence between the policies, the login policy and the parameterized target policy. And actually, they appear in a symmetric way. The KL, both KLs appear in both possible ways to choose the order in the two parameters. That's a very nice property, that interesting property that we found in this bound. And more importantly, those terms, the KL terms, are reward-free. They don't depend on the rewards, which means we can plug the missing rewards data into them. We can take advantage of the missing rewards data for those terms. And that inspired these learning objectives that we used. We can call them reward-free regularization. That means these quantities, the truncated IPS estimator for the risk, this can be evaluated from data. And then we add, a factor of the KL in one of the two possible orders, and that gives these two. One is called the KL, the other one is called the reverse KL. There's some literature mentions the name reverse KL. Basically, it means just put the arguments in the reverse argument, in the reverse order. That's what I mean. And of course, these terms, KL and the other KL, they have to be estimated somehow. So the bottom is just to show this is the estimators that we used for those terms, for the KL and the reverse KL. Not to dwell too much on the mathematics, but there were some nice properties about these estimators being asymptotically unbiased. It was one of them that was proved in the paper. It's a nice property. It somehow justifies that this is not a completely crazy choice of estimator for the KL. Moving on, here is a snapshot of the algorithm that we used. There is a lot in it, but the important part is that it takes in known rewards data and missing rewards data and a few parameters. And then at each iteration of the learning, what it does is it calculates estimators, one based on the known rewards data, another estimator down here based on the missing rewards data. And then it calculates the gradients with respect to the corresponding parameters. So one gradient for the one estimator, another gradient for the other estimator, and then the parameters are updated in terms of those gradients, right, with the corresponding amount of regularization. So that's pretty much what happens here, and ideally what we have at the end is a policy. Let's call it an optimized policy, but let's see about that. I mean, we find a set of parameters, theta. We find parameter values, theta, and then we have a policy corresponding to those parameters. We hope that it is optimal, right? That's the goal of the idea. At least let's see what kind of properties this algorithm gives. And by the way, the acronym S2BL corresponds to the name that we came up for the setting, semi-supervised batch learning. So that's the S2 is for semi-supervised, and BL for batch learning. Semi-supervised, there is something about this work that took inspiration from methods that have been developed in semi-supervised learning, where you have labeled data and unlabeled data, right? And there is a similar theme that taking advantage of the unlabeled data makes it possible to learn something better than if you used only the labeled data. And the WCE name is for weighted cross entropy. It has to do with the form of the second estimator, but that's just a name. Okay. So we did experiments and sort of like prototyping kind of experiments just to see what happens. We used benchmark classification data sets with an established strategy called supervised to bandit conversion. That means you have a supervised learning data set, is labeled data, but you convert it into something in which you're going to evaluate policies. We tried two kinds of target policies. Both are softmax kinds of policies. You can see that in the form, in the exponential weighting form of these policies. One is collinear. Why? Because it is it is linear with respect to some appropriately defined features, depending on the actions and context. And then you need to learn this parameter, that's the linear form corresponding to that policy. And the other one, let's call it neural. It means that the function that you put here in softmax is the output of a neural network, some kind of architecture. And the login policy, in all cases, was chosen to be a neural network. It was a ResNet. And the choice for that had to do with the previous literature, because we needed to be able to compare to previous results and be able to compare apples to apples, so to speak. So then somebody had said that, that precedent, so it was good to use it for comparison purposes. And this login policy, by the way, so there is a neural network. It was a ResNet, and that neural network, so the output of that neural network is plugged into softmax, and there is a temperature parameter here, which is useful for modifying the quality of the login policy. You can create a login policy that has more accuracy or less accuracy on this data. And then by doing that, you can then compare the quality of the output policies learned by our methods compared to the quality of the login policy. And here is a snapshot of the results. Normally, I like to show pictures like plots. For this work, those plots are kind of underway. It's work in progress. So I apologize for, sorry about that, for presenting this table. But the important part about this table is that, so here are results for both data sets, Fashion, MNIST, and CIFAR-10 that we used. The different columns are for the different methods. The first few are our methods, starting from BanditNet. The BanditNet is the method from the 2018 ICLR paper. And the last column tells you the accuracy of the login policy. By the way, the numbers in this table are no longer like the rewards as they were defined, but they are accuracies. Since these are classification sets, we can use a very intuitive notion of quality, the accuracy. And so something to highlight is how, by the way, here is a temperature parameter in the login policy that affects the quality of the login policy. And also there is another parameter, rho, that controlled the proportion of, so these data sets are completely labeled. So in order to turn them into data of the kind that we wanted to consider, known rewards plus missing rewards data, so we had to ignore the labels from some part of the data. So this raw parameter controls the proportion of data, known rewards data versus missing rewards data. And I guess something nice to see is how the quality of the login policy can be, well, it can be kind of high, it can be kind of average or kind of bad according to the chosen temperature parameter and also according to the difficulty of the data. But it seems that in all cases, look especially at the first column. This is the method for the algorithm that I showed in the previous slide. It seems like learning a policy by these methods with the reward-free regularization improves the accuracy by a little bit, at least by a non-trivial amount. And that was something very interesting to observe. So here is a learning method that can take advantage of these two kinds of data, the known rewards data and the missing rewards data, and it can learn something that improves the accuracy, even if the accuracy of the login policy was not so good from the start. Good. So that's pretty much all. A few concluding remarks. I've talked about this setting, the semi-supervised batch learning setting, where there are two kinds of data. There is the non-rewards data and the missing rewards data. We did reward-free regularization for taking advantage of the missing rewards data, and as I just showed in the little table, something reasonable came out. I mean, something interesting came out, at least, of those experiments. Now, this is a time where normally I would acknowledge my co-authors, but as I said, this is work in progress, and also I prepared these slides in a bit of a rush. So I do want to acknowledge Golamali Aminian from the Turing Institute. So this is the other person who led this project together with me, and there are a few others that I will do a better job at acknowledging them at another time. Thank you very much.